Why triangles make structures unbreakable. Welcome back to Blueprint to Reality, the channel where simple shapes create powerful structures. One shape appears again and again in bridges, towers, roofs, and cranes. It's not a curve. It's not a square. It's the triangle. Today we answer a fundamental engineering question. Why do triangles make structures unbreakable? Introduction. At first glance, a triangle looks ordinary. But in engineering, it is one of the strongest and most reliable shapes ever used. From ancient trusses to modern space frames, triangles are everywhere, for one simple reason: they don't change shape under load. In this video we'll explore the geometry behind triangle strength, why other shapes fail, how triangles control forces, and where engineers use them in real structures. 1. Shapes under load. A simple comparison. Let's compare basic shapes. Squares and rectangles. Joints rotate easily. Shape distorts into a parallelogram, requires extra bracing. Triangles. Fixed geometry, no internal movement without changing member length, naturally stable. This geometric stability is the key. 2. The geometry that makes triangles strong. A triangle is defined by 3 sides. Engineering truth. Once side lengths are fixed, angles are fixed. Shape cannot change. Forces are locked into place. No extra bracing needed. 3. Force flow inside a triangle. Triangles manage forces efficiently. How forces move. Loads enter at joints. Members experience tension or compression. Forces travel directly to supports. There is minimal bending, and bending causes weakness. 4. Tension and compression. The perfect pair. Triangle members work in 2 ways. Compression members push forces inward, often thicker or shorter. Tension members pull forces outward, can be slender but strong. Triangles separate these actions cleanly. 5. Why triangles resist deformation. To deform a triangle, you must stretch or shorten a member that requires significant energy. This resistance makes triangles ideal for earthquake loads, wind loads, dynamic forces. They don't sway easily. Fix triangles in truss systems. Trusses are networks of triangles. Common truss types: Pratt truss, Warren truss, Howe truss. Each design uses triangles to efficiently carry load across long spans. 7. Real-world structures that depend on triangles. Bridges distribute load over long distances. Towers and masts resist wind forces. Roof structures span large areas without columns. Cranes lift heavy loads safely. Remove triangles, and these structures fail. 8. Triangles versus heavy materials. Strength isn't just about material. Engineering reality. Geometry often matters more than mass. Triangles reduce material use. Lighter structures can be stronger. Efficient design saves cost and increases safety. 9. Triangles in modern engineering. Today's advanced systems still rely on triangles. Examples: space frames, geodesic domes, aircraft frames, high-rise bracing systems. Technology evolves. Geometry remains. 10. When triangles fail. Triangles fail only when connections fail, members buckle, materials degrade. The shape itself rarely betrays engineers. Details do. Conclusion. Triangles are not strong because they are simple. They are strong because they are stable. They guide forces cleanly, resist deformation, and turn simple members into powerful structures. This is why engineers trust triangles when failure is not an option. If this video changed how you see structural shapes, like, share, and subscribe to Blueprint to Reality. Comment below. Which shape should we break down next? At Blueprint to Reality, we turn geometry into strength. See you in the next video.